Okay, so this morning we've been learning about optimization for a single core, optimizing how your code is executing on one core of the CPU. And of course that's important, but probably most of what you're going to run is not only executing on a single core, it's a parallel application. And a parallel application, unless it's particularly simple, is going to need communication between the different processes that are running. So they will need to exchange data because they're all doing Halo updates and so on, or whatever. And the bottleneck in your code, every code has a bottleneck that stops it going faster. No code gets peak performance out of the entire system. And quite often that bottleneck may not be the compute. So optimizing the compute and going in and unrolling loop nests and blocking loop nests and optimizing for cache, whilst it may gain you a small amount of performance, it's not really the thing that's slowing your code down. So you don't know that until you start profiling, and we'll understand profiling a little bit more tomorrow. So in this lecture, I'm going to talk about another aspect of what may be slowing your code down, and that could be the communication, the MPI. And typically, if you have a problem that you wish to solve, and your problem is a certain size, and you could solve that problem using a few nodes, and if you do that, then a few nodes, there isn't much communication because they're only sharing data between a few of them. But it may be that you either want the problem solved quicker and you want to use more nodes, or that the problem's quite big and you can't fit it on a few nodes because the nodes only have 32 gig of memory each. So in that case, what you're going to need to do is use more nodes. And as you go to using more and more nodes, then of course there's got to be more and more communication, and there's less and less local computation because each local node is only processing a reduced fraction of the entire problem. So the balance can shift, and quite often you can say, oh, well, I know my code is compute bound, but that might only be true when you run on 5 nodes or 8 nodes. But when you go to run the full problem and it's on a much bigger thing, you may be looking at the network. So it's very important to track how these things change and not sort of blindly characterize your code as it's always compute bound. So this isn't going to be an introduction to MPI. I'm not going to teach you how to do MPI. I mean, that's a course in itself. But what I'm going to tell you a little bit about is how MPI is implemented and specific implementation things for the Cray XC30 and some things you can do to help improve performance. Now, the best way to improve performance is communicate less. And you should try and optimize whether or not data needs to be communicated, but ultimately, you get to a point where you can't communicate any less, and then what you would like to do is to get the best performance you can, given the constraints of what you're trying to do. So the first part will be about some general MPI stuff, and basically you can see this as being what's happening in terms of MPI between CPUs. But a particular feature of Daint is, of course, that it's a GPU system, and if you're running a GPU code, you've probably got a lot of data residing in the GPU memory, and you'd like it to stay in the GPU memory. I mean, the big optimization that when you use a GPU is not to move data backwards and forwards between the CPU too much. And when you do it, to do it as smartly as you can. So there are some specific tricks that you can use when you've got GPUs attached to your nodes, and I'll talk about those at the end of the lecture. So, as I've said, parallel codes communicate data between processes. That's just what they do, unless they're embarrassingly parallel, and that's a very small subset of the type of thing you're doing. And if you really do have an embarrassingly parallel problem, maybe Daint is not the ideal machine. I mean, because, it's part of the cost of that machine is a really good network, and if you clog the machine up and you're not using the network, you could get equally good CPUs in a workstation and do it that way. So the communication cost depends on the network. By cost, I'm not talking about money, I'm talking about time. Or memory system for shared memory communications, and that's something I'll just talk a little bit about as we go through. So 2 factors determine the cost, and this is what I was talking about yesterday. You've got, if the internet is a sort of set of pipes, then you can think of the interconnect as well as a set of pipes, and you're putting water through them. And the two things that limit stuff are, when you start pumping, how long does it take for the first bit to get out of the other end? How long is the pipe? And that's the latency. How long does it take when you first start sending data until the first data arrives? It's the latency. And if you're sending very short messages, latency is everything. But if you're sending a big message, then latency is the time it takes for the data to start arriving. But once it's started, at what rate is it coming in? And then you've got bandwidth. And yeah, the bandwidth is the thickness of the pipe. You can tune that by just buying thicker pipes. You know, CSCS have, in the optical network, they've got a full optical network, so they've got the fattest possible bundle of fiber optic cables. Other systems have spent less on their interconnect, and they spend less on the fiber optics, so the tubes are thinner. So they get less global bandwidth. Latency is more difficult to optimize. I mean, yes, better interconnects give you better latency, but latencies have been sitting at around a microsecond. You can do slightly better in certain circumstances with the Cray Gemini. I think you can get 700 nanoseconds for Shemem puts if they're the right size and so on. But essentially, we're reaching a sort of hardware limit there, and latency isn't going to improve by vast amounts in the foreseeable future. Whereas bandwidth, you know, you can pay more to get higher bandwidth. So decisions made by the application developer can affect the overall performance of the application. Well, you know, that's a sort of, in one sense, that's completely obvious. But there are ways to change your existing code where you can get better performance doing the same operations. The size of the messages affects how important latency and bandwidth are. So, as I've said before, if the message is small, the network latency is dominant. So, depending on what you're doing, if you can, using larger messages will reduce the number of times you pay the latency penalty. So if you send 1 byte of data, you know, you send a 1 byte message, it's just latency is what you pay. And if you have to send a megabyte and you do it as 1 byte messages, you will pay a lot of latency costs. If you can put them together, you will pay less. And MPI is all about large messages in general as a programming model, whereas something like Cray, Fortran, and Shemem are much more targeted at small messages because they're single-sided and there's less overhead in sending those small messages. So nodes have got fatter. You know, a long time ago you had 1 core per CPU or 2 cores per CPU, but now the number of cores per CPU, depending on whether you count hyperthreads as cores or not, but even so, we're up at the sort of level of 10 to 20 CPUs per node. And this is going to get worse. I mean, as we go to Xeon Phi, you've got many, many more cores on the system. And the power budget and the power envelopes are such that we're going to see more and more cores. So it's difficult to scale those codes across the whole CPU, just within one CPU. And there are things like Numa effects. As I said before, you don't need to worry about Numa effects on a single Sandy Bridge node, as like you've got here. But if your library is done well, or if you, as a programmer, explicitly use a shared memory programming within the node, sharing data between the cores on the CPU is much faster than sharing data between different nodes. Because you're not going, I mean, the Cray, you know, I will tell you the Cray Aries network is the best thing ever, but it's not as good as just exchanging data within the memory of the CPU. So you can optimize your application performance by thinking about maximizing communication between the cores of a CPU. So one way you might do that is if you might decide that instead of running one MPI rank on every core, you will run one MPI rank per node, and then use OpenMP to thread across the cores of the node. Or you'll run two MPI ranks on the node, and you'll have 4 threads per rank. Now, of course, that means changing your code. If you've got an MPI code, and what you've done is you've got a big array, and this array has been split into chunks, and you're doing some sort of updates, and there's going to be halo exchanges with the nearest neighbor. If you just kind of split the whole thing into chunks and then just put the chunks on the node using the default layout, what you will tend to get is that so you have a big problem, and you split it up with MPI. So you split it up into 16 parts. And you're going to run this with MPI. So each process is going to have one of these squares, and it's going to need a halo because it's going to do some little stencil. So it needs to know what the nearest neighbors are doing. So you'll have one here, and the next MPI rank is going to be doing this one, and so on as you go across. And if you look at how these ranks are numbered, how should you put those ranks onto a CPU? Well, there's 16 ranks here, so I'm going to need 2 Sandy bridges, assuming I use 8 ranks per node. What I could do is just do nothing and just say, run it. And what will happen then is that these ranks, 0 to 7, will go on the first CPU. These ranks, 8 to 15, will go on the second CPU. OK. But then you look at what sort of communication is being done. And if I just look at one of these ranks, so if I look at number 5 here, it's going to need to talk to number 1 and number 4 and number 6 and number 9. Now, some of those communications are on the same CPU because ranks 4 and 1 and 6 are on the same CPU, but rank 9 isn't. It's on a different CPU. So in general, when you try and work it out, what you want to do is not put a strip of these onto the CPU, or one CPU. What you should instead be doing is trying to put a block on. Now, I've chosen a very simple example here, and so this isn't, just looking at these numbers, it's hard to see whether there would be a benefit to reordering how the ranks go on. But if you were thinking about a very large problem, and you were thinking about very large cubes, so you've got a cubic problem, and this has all been divided up. And then it's been divided up again, so I've got all of these different ranks. Rather than putting a strip onto one CPU, what I should do is I should take a 2 by 2 by 2 cube of ranks. That's and those aren't consecutively numbered in terms of ranks because these are going to be 0 and 1 and 4 and 5, and then this will be number 15, and so this one over here is number 16 and 17, and 20 and 21 are behind here. Those sets of 8 ranks there form a little 2 by 2 cube within my problem. If I put that 2 by 2 cube onto a node, I get more on-node communication than if I just laid it out as a long strip of numbers. and done it that way. So thinking about which nodes are talking to which other nodes and trying to maximize how you can reduce the amount of communication off-node by making it as cubic as possible if you've just got a simple decomposition is very important. And that's because if you look at this is, if you look at within a node, how long does it take to send a message from one rank to another? This is from one core to the other. And if you look at here, so this graph is showing you as the message size increases across the bottom, the green is time, the time it takes for that message to go in terms of microseconds. So as the message gets bigger, the time takes longer because eventually you've got a straight line here, if it weren't logarithmic, but you'll have a straight line here because you're just bandwidth. The more data you send, the longer it takes. When you get down here, it's flattened off because of latency. That no matter how small the message, it takes a certain amount of time just to get the first bit there. Or if you like, you can convert this to bandwidth. So green, obviously, up is worse because up is more time. Bandwidth, the bandwidth down here is small because you're just being hit by the latency, and then the bandwidth increases, and you get strange effects at various different things here because of things called protocol changes. But if you look at the same thing here where I'm sending messages between nodes, same graph, but if I put them together, so now it's quite hard to start reading the numbers, but they're the same scales here. This is within the node, and this is between nodes. So you can see that the green is higher than this, and the bandwidth that you're seeing is much lower when you're going between nodes than when you're on the node. And that's because the MPI library is using shared memory optimizations. So wherever possible, and of course you can never arrange that all of your communication is on the node, but it's worth thinking about, can I arrange that as much communication is on the node as possible? And this does not mean rewriting your application, because you can do all of this at runtime. You can arrange how the ranks are mapped onto cores at runtime. So yes, within the node transfers are much better, but that relies on having a shared memory machine to do these transfers in shared memory. And we know that SMPs don't scale shared memory machines. So eventually you reach the point where, yes, you've got an SMP node, you've got a node that shares the memory, but you're going to need to hook this together. And messages that go between other nodes are going to have to use the network. And then within the Aries, there's various optimizations that are done to try and get the best performance that you can. And so within the Aries, there's an Aries chip that's making all these decisions. There's two ways it can send messages. One is called fast memory access, and another is called the block transfer engine. Now, do you need to care about this? Well, you might be interested, but you might not. But the reason that this is interesting or relevant is because the way that these methods work tells you something about what you can expect to get if you send messages in these different ways. And which way a message goes on is not random, it's determined by the size of the message. So the fast memory access method of sending data is the best in terms of it gives you the lowest latency, and you can have more than one transfer active at the same time, which of course is very good if you've got 8 ranks on your CPU all sending messages. The downside is that the CPU is involved in the transfer. So the CPU has to do some work. I mean, MPI, if you know anything about MPI, when you send messages, there's a sender and there's a receiver, and there is some synchronization that has to go on between those, and this is all to do with tags that label messages so that they know that I'm sending this message and that is the message that this other one should be receiving. So there's all sorts of things called tag matching that have to go on. There's computation that's associated with this. So the CPU is involved in the transfer because some of this processing goes on the CPU. There isn't a dedicated CPU within the Aries that does all of this. And what this means is that messages cannot travel asynchronously, and we'll come to this again in a bit. The other way you can send data is the block transfer engine. In this case, the CPU isn't involved, so the Aries can do a lot more itself of making sure the messages get delivered. And it can give you better point-to-point bandwidth. But the latency is higher, and the block transfer engine, as I say, this is being done by the Aries silicon, and the Aries silicon is shared between all the cores. So there is possible contention, and you could end up with messages being queued because the block transfer engine is busy with doing work for the other cores. So the block transfer engine works by this thing called remote direct memory access. And this basically means that if the Aries network, and Gemini for that matter, but if the network wishes to put some data, give it to another rank, it can access the memory associated with that node without that node doesn't have to do anything. This node, via the network, can just go straight into that memory and put it. So the remote side CPU doesn't have to do anything. And the block transfer engine takes advantage of that. And if you're doing PGAS type languages, if you use Core, Fortran, or Chemin, that's very important. Now, that's okay between nodes with the Aries network, but when you do things on a node, if you're running one rank per core, these are essentially running, they've got separate address spaces, and the memory tends to be insulated. So in order for this to work, you need to somehow provide a mechanism to expose windows of memory belonging to other ranks in order for the shared memory optimizations. And this is done by something called XPmem. You don't really need to care about that at all. It's just what it is. If you look at module list, you'll see some module associated with that you should never touch. But this is an optimization, and this is why you get this much better performance when you do things within a node. This XPmem enables it. And of course, this means internally that you have to do special things with the address spaces to make sure that they've been made visible for doing this. So if you look at an application that's executing, so here I've got two ranks, if it was MPI, and they're going to do some compute and they're going to do some communication. So on one rank, I'm going to do some computation, and this will prepare some data, and I will then want to send it to the other rank. There's then some more computation, and then there's a checkpoint. And by checkpoint here, I don't mean writing to disk. What I mean is that at this point, I need the results that have arrived from the other rank. I need them to be ready by this point in order to do this next bit of computation. In MPI, it would be a barrier. And so the picture that you have is that you do this sending of data, and this will happen in the background. And later, all you need to do is later on, you will just check that it's arrived, and then you will continue. So you're overlapping the communication with the computation. And that's kind of the holy grail of what you're trying to do. Communication costs you in your application. You can never get away from it. You have to send data. You can try and minimize the amount of data you send, but eventually you reach the point where I do need to send this data. So what you're trying to do now is trying to mask the costs of that by hiding the communication time behind some local computation. And that means getting the data ready as early as you can and sending it as early as you can before it's going to be needed by the remote CPU. And then it will, by the time it needs that data, it will already have arrived. And this is the picture that you kind of have of what's going on. And if you've done the MPI programming, you've got MPI I send and MPI I receive, and these are non-blocking communications. The trouble is, this doesn't always happen. And probably most of this talk is basically about why doesn't it happen, and there are solid reasons why it doesn't, and what can I do to improve matters. So, is there anybody that's actually using any of these PGAS languages? You should try them, but most people have an MPI code. There are cases where putting in, say, Fortran coarrays or coarray C++ can give you performance benefits within a larger MPI application. But I won't talk about this if people aren't interested. The main problem of these, and all of these PGAS languages, is that everything is very single-sided. It's one-sided in that I will send this data to this other CPU, but it won't know it's arriving. Or I will get data from that other CPU, but it won't know that I've taken the data. So of course, this will only ever work if you make sure that you have the right synchronization points in that mean that I won't try and pull data from over on that node until the data is ready on that remote node. So there's all sorts of synchronization patterns. And it gives very good potential for overlap, but you have to think a bit harder about the synchronization. MPI, because you have a sender and a receiver, and they both have to make a call in order for the message to be transferred, it makes it easier to use because there's an implicit synchronization. You think much more about the synchronization, and that makes it easier to do. But this additional flexibility of MPI means that there has to be, if I just pull data out of that processor's memory to me, that other processor doesn't have to do anything. I just take it out because the Gemini or the Aries network allows me to do that. It just gives me visibility to pull it out. In MPI, there has to be a handshaking that goes on, that there's a call to send and a call to receive, and they must match. So the remote CPU has to be involved in that process somehow. And what happens is, when you think about it, somehow you have this picture that the MPI library is just running. And as a message arrives, it matches it with your receive call and puts it into the buffer. And when you do the MPI barrier, all it does is check to see if that message really was ready. But that's not what happens. The MPI library is being executed by the CPU. So the MPI library can only do MPI tasks, MPI housekeeping, when the CPU is executing code in the MPI library. And if your code is just computation and you're just doing some wonderfully unrolled loop nests, and you spend a lot of time in doing that, the CPU is devoted to that task. And it's not executing any MPI library code. So message, it's not busy receiving data and matching messages. Actually, what you think of as a non-blocking MPI call and you think you're getting overlap, what really happens is the data kind of arrives at the Aries on your node, but then it's just sitting there because the next stage of processing cannot happen until the MPI library is the thing the CPU is executing. And if you haven't called MPI, it's not doing that. So the message is just sitting there. So then you say call MPI barrier, or call MPI wait all to complete the messages. And normally you'd think of that being just a check that everything has indeed arrived. But what it really means is that suddenly all of these messages that have got queued up, now you've told the CPU to go into the MPI library, and then it has to do all of this stuff So you'll see if you look at a profile that, God, it's spending a lot of time in wait all. Why is it spending so much time? You know, I sent this data ages ago. And the reason is that you're not, if you never go into the MPI library, it can't do all of this matching. So again, we're going to talk a little bit about what you can do to help things along. The Cray MPI that you see is a fairly standard distribution. Cray don't write their own MPI from scratch. It's basically the MPitch library from Argonne. It's MPitch 3. What Cray do is, down in the lower layers of the library, they change some of the code to take advantage of specific features of the Aries network. But if you actually ever were to look at the code, and of course you can't, but you know, Cray has not rewritten vast portions of the library. There's probably 5,000 or 10,000 lines of code that are Cray specific, and the rest of it is the standard MPitch distribution. It's a good, robust MPI implementation. It's well tested. And as I say, you know, at the lower levels, there are some optimizations that Cray puts in. Within MPitch, you can plug in some additional modules, and one of the modules that Cray uses is something called the Nemesis module, and that's one of the things that, along with the XP mem, helps you to get high bandwidth when you've got ranks on the same node. Again, you as a user don't really need to know that. So if you were doing MPI, what would you do? Well, you'd use non-blocking calls, and we would always recommend in any code that you should be using non-blocking calls. So don't be using synchronous send or anything like that. And what you should do is basically you'd say, I'm going to send data from rank A to rank B, and I'm going to send data from rank B to rank A. So as soon as the data is ready, rank A will send it to rank B. Rank B will need to make a receive call in order to get it. You will get better performance if the receive call has been made in advance of the data arriving. If, assuming various various conditions are met, assuming those are met, if you have told the MPI library locally, when this message arrives, it is going to end up in this array. You know, when you've called MPI receive, you've passed it in a particular buffer. And if you've told it what that buffer is, and it knows about it in advance of the message arriving, it is much more likely to put the data directly into that buffer. If it doesn't know where it's going, it will have to put it in a buffer within the MPI library and wait until you tell it where to put it by doing the MPI iReceive call. So we would always recommend that you do your MPI iReceive calls as early as possible, because the MPI library then knows where the data is going to end up, and that means it can avoid using additional buffers within the MPI library, which will then need another data copy. All right, it's a data copy within memory, but it still takes time. So post your receives as early as you can. So this message then will go across here, and then you do an MPI wait all, and that's the barrier where you will make sure at that point you know that that message has completed. And then you will get nice overlap between these. But this is not always possible in the application, and it's not always possible because of the way MPI is written. And this is what I've said before, is that even though I receive and I send are asynchronous calls, it doesn't mean you get good overlap. So putting your MPI iReceive early is important. The other thing is that the CPU has to help, because matching message tags to know that of all the messages that are coming in, which message goes in which buffer, there's a matching that has to go on. And this can only happen when the program, your user program, has called some sort of MPI routine. It doesn't have to be the right MPI routine, because the MPI library is pretty smart, but somehow you've got to be doing some sort of MPI operation. And whilst you're there in the library, it will also progress some messages. But if you never go into that library, you know, if the first time you go into this library is here, you could well end up that nothing really has progressed until you hit this point. So to get around this, there's different ways that messages can be sent, and these are called protocols. And the two main ones are what's called eager and rendezvous. And what I'm talking about first is the eager protocol. And that this is where, this is where the MPI library can actually have a little buffer, so that if you send the data, it will go into an MPI buffer. So from you call the code with your buffer. It will be copied into a buffer within the MPI library. It can then be sent across the network into a buffer at the remote side. And then when you do the receive, the data will actually move into the buffer that you called MPI receive. So the MPI library is using its own buffers to try and get, so the messages can at least get across here, and then they're local. So when you call the receive, because here these are blocking, when you call the receive, you've only got a quick local transfer to solve the problem. Now, of course, the MPI library doesn't have infinite space. You've only allowed it to have a certain amount of memory because you actually want to run your application with data. So you can't, it doesn't have an infinite amount of buffer space. So this will only work for small messages. And if you send too many small messages and they're all outstanding, meaning that they've not done this final stage of getting across here, if you fill up all these buffers with all your messages, then any further messages are going to block. And what that means is not that, oh, the data just gets lost. It means that the MPI library, the data will be queued up on this side and won't have got across here because there's nowhere to put it locally. So as long as you're not sending too many of these messages and not getting that final stage done, this can be a way to get a good overlap. And so a better way to do this is with non-blocking sends. And if you do the non-blocking sends, just like we showed in the picture before, except the difference now is that we know that the messages are small, what we find is that when you do the send, the small message goes into the MPI library, it goes straight across and goes in, and basically the Aries here is asking, you know, it asks the remote MPI library, do you have a spare buffer? And if it says yes, then the data goes across into that buffer. And then when you come to the wait all, it's a very quick transfer across there. So then you really do see overlap going on. And the same in the other direction. And that's eager protocol, that's for small messages. But for larger messages, there just isn't space in these buffers in the MPI library to do things. And if that's the case, and this happens automatically, you don't have to tell it which way to do it. If that happens, what now has to happen is basically when you do a send, nothing can happen. The data cannot be buffered. It's going to have to go into the final destination. So nothing can happen until the MPI library at the receiving end knows where that is. So if you don't call MPI receive for ages, nothing happens. But then what happens is that basically when you do an MPI send, a tiny message is sent saying, look out, big transfer coming, are you ready to get it? It's got this tag. And then at this end, nothing happens until the receive is posted. And at that point, it knows what the data is, and it sends a request and says, right, I'm ready for the data now. The data comes straight out of this, you know, your application memory, straight into application memory. There's no buffering in between because there just isn't space to buffer these big messages. And this is blocking here. These are blocking calls, so you can see that, you know, the time spent for these transfers is quite long, and nothing will happen behind the scenes. Now, if you use the non-blocking calls in the MPI, and again, that's what we would recommend, what happens? Well, with Rendezvous for big messages, often what happens is at this point, you post a send here, going across from A to B, and what this does is it alerts B that there is some data ready to be received, but nothing can happen until you get down to the wait all, and then at the wait all stage, you will get progression of this message because you're not in the MPI library here, so there's no overlap. So for large messages, you're not seeing any overlap. You've written your code as if there is overlap, but you just can't get any because of the way the MPI library happens, the way that it can only progress when the CPU is not busy doing computation and goes into the MPI library to kind of match up the messages to say, so that at the receive side, it can then say, yes, I need the data, and pull it, basically pull it over. So when you profile the code, you'll see a lot of time in the wait all. So if you want to improve performance in your code, you would like to get more overlap between computation and communication. So what can you do? Well, the simplest thing is to say, try and get more of your messages to be sent by the eager protocol, the one that uses these little intermediate buffers, than by the Rendezvous protocol. Now, if your message is gigabytes, you can do what you like. It's never going to happen, but you can try. So what you can do is you can say to the MPI library, I mean, the MPI library, within the library, it makes a decision. It looks at the message size, and if the message is small, it will send it as eager. If the message is large, it will send it as Rendezvous. But this threshold isn't fixed. What it means is that if I make the threshold a bit higher, more larger messages will go as eager, but I will only have space in the buffers in the MPI library for fewer of them. So there's a trade-off. But if you've got a lot of messages that are quite close to the size of, they could have gone by the eager protocol, which would have allowed overlap, but instead the MPI library said, no, they're too big, I will make them as Rendezvous. If you change the threshold at which it makes this decision, you may get better performance. So it would rely on, if your messages, I mean, the default size for the decision is 8K. If you've got a lot of messages that are, say, 10K, they could have gone by eager quite well, but the library just didn't decide that. So if you know what your message sizes are, you can change this limit by this variable in your job script. It's not a recompile, it's just in your job script, and then you'll get better performance because it will allow it to use the overlap to do these. Changing this limit is not changing how much memory the MPI library is using or anything like that. It's just saying use larger chunks of your memory as buffers, so there will be fewer buffers inside the MPI library. So the advice would be, with your application, try and understand the buffer sizes, which you might be able to do just by looking at the application and knowing how much data is sent. Sometimes it's not as easy because of the way the code's written, in which case profiling tools like Cray can give you a breakdown of message sizes. Or you could even just use a trial and error. So the advice would be, the default for this is 8192. Try doubling it and see how the performance changes in your code. Obviously, if you're not using I send and I receive, you won't see so much benefit. But assuming you are, try doubling it. If the performance improves, try doubling it again. And just keep doing that until the performance levels off. Now, each message that's transferred by eager needs a buffer in the MPI library, and once all of that buffer space is used up, transfers will have to wait until there is space available, either because other buffers in the MPI library get emptied, or because you go to the wait all and it can flush everything out at that point. You can increase the amount of space there is for buffers. By default, the buffers are 32K each, and there's 64 of them. So you can't change the size of these, the units. So I mean, basically this is working in units of 32K. So the default is 64 times 32K, which is 2 meg. You can change this number from 64 to a larger value if you want. And this may increase performance. And again, you might want to try changing this. There is a downside to this because this means your MPI library is actually using more memory. So if you try and make this too big, you will probably end up with your job failing, saying it's out of memory, because you've just used more than 32 gig on the node. So I wouldn't try kind of just doubling this and doubling this and doubling this. I would make it a more subtle increase and see how that affects performance. So what we said before was that the main problem in all of this, in getting this overlap, I mean, Rendezvous can't really progress because the data has to be ready. But if you're not in the MPI library, nothing can happen because the CPU has to be involved in matching these messages. So the way around this is what's called the Nemesis thread, the progress thread. And the idea here is that you could get MPI to spawn a thread, and that's threads running on the CPU, but its only job is to execute the MPI library. So then, every time there is some task that's outstanding for the MPI library to do that needs to be done, you don't have to wait for your user code to go into the MPI library for this to happen. There's something that's in the MPI library all the time, and will just take care of these tasks as they happen. So this can do matching messages. It can initiate transfers. So in this case that we saw before, where we're going to send a large message by Rendezvous, and this large message, basically what's going to happen at the send side is it's going to say, I've got some data ready for you. And then at the receive side, it's going to say, OK, my buffer is ready for receiving the data, and the buffer is this address in the CPU memory. And at that stage, it's going to pull the data across. That would only happen when you went into the wait all library down here. But if you've got these progress threads running, they can start doing that earlier on, and you can get much better overlap. I mean, I suppose in your application, you could even write something yourself. You could use P threads or something, and you could have a thread that's just calling MPI probe all the time to just keep moving into the library, and that could be progressing things in the background. But that would involve writing something in your application. That's not the best way to do it. So this is within the Cray MPitch, that there is this progress thread that can be enabled to do things in the background. So each MPI rank starts a helper thread during the MPI initialization stage, and that helps the MPI engine progress. This isn't going to help you for eager messages. Eager messages didn't really need a progress thread because they were using these little buffers to get the data moved across the network and held locally until you took it. What this is important for is the big messages, the rendezvous messages. So if your code is only sending small messages and they're only going via eager, or you can increase the eager limit until they are only going by eager, in this case, you don't need to worry about this progress thread. But if you've got big messages in your code, and most MPI codes are constructed around large messages, then you might want to think about this asynchronous progress engine. So what do you do to get it working? Well, basically, you need to tell, in the job script, you need to tell the MPI library that I would like this progress thread, And the other complication is you need to tell the MPI library that there will be multiple threads associated with a rank that are accessing the MPI library. One of the threads is your application, just like before. The new thing is this progress thread that the MPI library is spawning itself. But either way, you need to set this environment variable as well. And if you don't do that, things will be nasty. And then you run your application as before. So if you're using -J1, which is the default on Daint, you probably need to do nothing else. Because by default, these, okay, you say, well, I don't want extra threads running on my CPU. They're going to interfere with my application. But what it will do by default is it will move those progress threads onto the hyperthreads that you're not using with -J1. And if the extra hyperthread is running something that's doing a very different pattern of computation, which an MPI progress thread is doing a very different thing to what your computational application is doing, these will work without interruption. They won't affect the performance in any noticeable way. If you are running with -J2, so you're running both hyperthreads on the core doing computation, if you run this progress thread, it is going to be competing with your application. And this could be more of an issue. It might not be much of an issue, and the benefits it gives you in the MPI library might be such that it's worth doing. But another way you can do things is using something called core specialization. And the idea of core specialization is, as we heard before, is that you've got 16 hyperthreads on the 8 cores of your node. So instead of using all 16 hyperthreads for computation, you could say -N 15, 15 user MPI ranks per node. There's one hyperthread spare, and you could use that to run the progress engines by using the -R flag to tell it to put those OS-type processes onto that spare hyperthread. So you would say -N15 -R1. Or you could say -N14 and -R2. Obviously, they shouldn't add up to more than 16, otherwise you'll end up overlapping stuff anyway. What's the right number for -R? You have to try it, really. 1 or 2. You can set -R up here, and you can probably set -R up here to be 8, if you like, because there's 8 spare hyperthreads. But down here, where I'm using all the hyperthreads because I'm using -J2, then you maybe need to experiment. But it can give quite a good performance boost by enabling this. So even though I'm using less of the CPU silicon for computation, computation wasn't the only bottleneck in the code. So doing a little less computation per node, but using the additional silicon, this additional hyperthread to do some MPI progression is a useful benefit. So MPI is the library that you're probably most likely to be using, but language, the Aries interconnect is not MPI. If you were to delve down through the MPI code, the MPI library, you'd find that MPI on the Cray systems is built on top of a different library, a lower level library called Dmap. And Dmap is much closer to being the native language of the Aries interconnect. So you as a user probably don't want to call Dmap. You can, but you probably don't want to. But that's what's going on underneath. And within Dmap, the Dmap library, there's lots of clever optimizations that have been done that are specific to the Aries network. So when you do things like collective operations, MPI all-to-all, MPI all-reduce, MPI barrier, things where you have to have cooperation between all of the ranks in your application. So they've all got to talk to each other. there are good ways and bad ways to do that, which is why you should never try and write your own collective and not use an MPI collective, because they're optimized in the MPI library. But they're even more optimized underneath that in the Dmap library. So what you can tell Cray MPI to do is to use these optimized Dmap collectives. So if you profile your code and you see a lot of time is spent in these collective operations, so Cray Pat or however, then telling it at runtime that it should use the even more optimized Dmap versions underneath. No change to your code, you're just telling the library to work in a different manner. You can get better performance. In order to do this, the only difference is when you link your code, you have to explicitly link in the Dmap library. So if you don't do that, you won't be able to take advantage of these. So it would require relinking your code. You don't have to recompile it, you just have to relink it so that the Dmap library is available to do this. And you can get further acceleration if you use if you set this other environment variable. When is it a good idea to do this? Well, you must be spending a lot of time in your collectives. So look at the profile, and then probably the best thing to do is to try it. When is it a bad idea? It's probably never a bad idea. There may be cases where any of these optimizations, and I mean, within the that's at the Dmap. Within the MPI layer, the MPitch, I mean, Cray has done optimizations in the MPI code as well, so that when it does a reduction, it does it in a way that is sensible for the network and the CPU. So, you know, if you've got an Ivy Bridge CPU with 12 cores per CPU, doing a binary tree reduction is not a good idea because you haven't got a power of 2 number of cores on the node. And you're trying to optimize as much communication on the node as possible. So you really want to do a reduction of 12 on the node and then reduce across nodes. For Sandy Bridges 8, it is a power of 2, but that's, you know, that's an example. So within the MPI library, there are optimizations like that that are being done for the collectives. And again, these are on by default, whereas the Dmap ones are not. It's all a question. I would say try it. I would try both and see. If it makes a difference, use it. If it doesn't, don't. It's unlikely. I think the Dmap collective probably isn't going to make the code slower, but I would try it. Possibly, but I don't think it'll fail, in which case you probably just don't see an improvement because it just falls back on the MPI library. The optimizations that are done in the MPI, there are cases where the optimizations are not, they actually don't improve your code performance. And the way you might see this is if you run on 2 different systems and you run on a cluster, and there the all gather doesn't take, you know, it takes a certain amount of time, and you've got a Cray system, and the all gather is taking a larger proportion of a larger amount of time, and you might say, well, that's a bit weird. I thought this was supposed to be a good interconnect. It could be that these optimizations are, you know, like any optimizations, they rarely work for every case. So they look at the cases that are most common and they optimize for that. If your case is slightly different, you know, the thing you're doing, the data structure you're doing an all reduce on has a particular form, it may be that these optimizations are making things worse there. So you have the option to switch these off. So if you do see that, well, the all gathers did seem to take more time than I expect, try switching this off. But also file a bug and say, switching it off made a difference because, you know, these optimizations can be improved within the library. And especially if you're using all routines, like I say, it's based on the number of ranks. You know, if you're calling with COM world, it probably works fine. But if you've got a strange subcommunicator you've created, this is where the optimizations may not may not have been worked through. So I don't know how much you know about how memory is used within, say, Linux, but you have this idea that pages of data are brought into memory as a sort of almost like a cache. You've got this translation look-aside buffer that pulls in a page of data. So when you ask for one piece of data, if it's not in the cache, then it goes to the next level of cache. And if it's not in that, and eventually it says, OK, and it pulls a whole page of data into memory. And this page has a certain size, which by default is 4K. Now, if you're doing random access of memory, small pages is probably not a bad idea, because you're only using one piece of data, and then you're going off to a very different part of memory. But if you're doing something in a more scientific application where you're processing a whole array of data, you're not just going to use this piece of data. You're going to have this sort of spatial locality that I'm actually going to be processing loads of neighboring pieces of data as well. So it actually makes sense to load in larger blocks of memory as these pages. And these are called huge pages. Because there is a time taken to actually load the page in, loading larger pages can give you better performance. And by default, when you compile a code, it is not using huge pages. But by default, actually, the MPI library is using huge pages. You don't have to tell it that. It's automatically doing it. But how big are these pages? Well, the default is 2 meg. Do you know, Alfio? 2 megabytes. But you can change this at runtime by setting an environment variable. So it is probably a good idea to just try increasing this. What sort of values should you try? 8, 4 and 8, 16, something like that. You very rarely see better performance by going right up to the high limit. You can try it.
But there is also a module.
Yes, but that's for user code.
Yeah,
the huge pages is automatically used for the MPI library. So regardless of that, you can try changing that without any, you don't have to recompile your code or anything. And it's probably worth exploring that. Now, I know I'm saying there's all these things it's worth exploring. And it sounds like this endless list of things you should try. But it probably is worth, taking an afternoon and throwing together some jobs with just different variations of these and just see which is giving you the best performance. You're unlikely to have to repeat this very often with your code. But if you can spend an afternoon, but you get a 10% speed up, and you're going to be running this application for the next year, it's an afternoon well spent. I mean, I can give you sort of ideas about when you might try it. Here, I would try it. I mean, there's no way to say whether it's going to be good or bad. I would try it, because different applications just work in different ways about how they use things. For non-MPI codes, I don't really mean for non-MPI codes. What I mean is even if it's an MPI code, so huge pages can improve your application performance. So when you build your code, you might want to use huge pages for the whole application. And again, this isn't specifically MPI, but this is something that you should try. And to do that, you will need to rebuild the code, recompile it. So after you make clean, you load a Cray PE huge pages module, and there are Cray PE huge pages, and then there's 2 megabyte, 8 megabyte, 16 megabyte, whatever you like. And you rebuild the code. So you need this module loaded at compile time, and you need this module loaded at runtime. And again, what am I going to say? You should try them all. Probably I would concentrate on 2 megabytes, 8 megabytes, 16 megabytes. I wouldn't worry about the very small ones. They rarely give benefit. Going beyond this, you can try them, but they're not often the best. Now, if you've got a large code that takes many hours to build, and I've just told you you have to rebuild every time to do this. That's not very good. There is a trick here, and the trick is that how are these modules actually different? And the answer is they're different in one environment variable. And if you do module show for those, you will see which environment variable it is that is different. So you can compile your code with one of these loaded, and you can then run with a different one loaded to see what happens. So you could compile with 2 megabyte pages, huge pages, and you could run having loaded the 16 megabyte huge page module, and that will actually be using 16 megabytes, because the only difference is that it's changed the value at an environment variable that only has an effect at runtime. So again, this is one rebuild of your code and then a few experiments. It is almost certainly worth doing that. So you have this idea that huge pages is on for the MPI by default because it always gives benefit, but it's worth tweaking the page size at runtime. It's not on by default for applications. Why, I don't really know, because if your application goes slower having compiled with huge pages than with 4K pages, as far as Cray is concerned, that's a performance bug that you should file immediately, because something is wrong. It should never be slower. That's the kind of the party line. Obviously, we'll come back and say in some particular circumstance there is a very good reason for that. But for the sorts of codes that get run on Crays, basically we never would expect huge pages to be slower. So definitely within your user code, you should also build with this and do the experiments. Now, all of what I've said is true whether you have a pure MPI code or whether you have a hybrid code that's MPI with each rank having some OpenMP threads. So what I'm talking about here is not going to be about, if you like, performance optimizations or ways to improve performance. What I'm going to talk about here is if you have a code with OpenMP threads and MPI, how are the threads going to call MPI? Why is this important? It's important because you have to make sure that you don't screw things up. Because if your MPI library is not thread safe, if 2 threads from the same rank try to call the same library, you could get all sorts of nasty things happening that could cause the library to deadlock, it could cause messages to get confused, it could cause all sorts of problems. And you want to avoid that. So if different threads are going to be calling the MPI library, you want to make sure that you don't get these conflicts. So the library has to be made what's called thread safe. But in order to do this, inevitably, you're going to have to put some locks in the library to make sure that only one thread does this at a time, because if they both try to do it, it's going to crash. So there has to be a locking mechanism inside the MPI library. Anytime you've got locks, there is a potential slowdown. So the more safe you make your library, the more potentially there could be a slowdown. So within the MPI library, you can specify, the MPI standard as well, you can specify different levels of thread safety, which will require increasing amounts of locking and have potentially higher overheads. So if you don't need the full amount of locking, you're much better off only asking for the degree of thread safety that you really need. And in order to know that, you just need to know how your application works. If you've got OpenMP code, so you've got parallel regions in your code that are threaded, but you've also got serial regions that are not, if you only call MPI in the serial regions, you don't need to worry. There's no conflict, because only the master thread, that's the only one that survives outside the parallel region, that's the only one that calls the library, and then there's no potential for conflict. And that's called single. And if you have no threads at all, you just have pure MPI, again, single is what you need. If MPI will be called inside the parallel regions, is it only called by one thread at a time? And if that's true, is it the same thread every time? Or could it be different threads? If you know any OpenMP, have you put your MPI call inside an OMP master region, or have you put it inside an OMP single region? If you've put it inside a master region, so it's always the same thread that calls MPI, then in the language of the MPI standard, you need funneled thread safety. If only one thread at a time calls MPI, but it could be different threads from time to time, you need serialized. And if it's the Wild West and every thread is calling MPI, then you need what's called multiple thread safety. And so if you've got an application and you've got this helper thread going on in the background, both of them are calling MPI, you from your application and the helper thread that's doing the progression. So that's why you needed multiple. So the MPI library has all of these different levels. The way you choose it is by, instead of calling MPI init in your code, you call MPI init thread, and you specify the level, which will be single, funneled, serialized, or multiple. I mean, they've got little names in capitals that you have to look up because you can never remember them. Calling MPI init thread with single is basically the same as calling MPI init. So there's two things. In your application, you have to call MPI init thread and ask for the correct level of thread safety. If you ask for the wrong level of thread safety, either if you ask for too much thread safety, there'll be a performance penalty. If you ask for too little thread safety, you'll probably get the wrong answers. Your code won't fail, you'll just probably get the wrong answers. Or you might lock things up. But as well as in your code calling MPI init thread, in your job script, you also need to tell it about the level of thread safety that you want by exporting this mpitch environment variable. The MPI library will not sort this out for you. You have to get it right. Yep. It will probably default to single. You've called MPI init thread with multiple, but you've not set the environment variable, so you get single. So I have a slide here. And basically what this says is that you will get, well, it's not obvious. There's nothing in the standard to say. I mean, this isn't a Cray environment variable. This is an mpitch environment variable. There's basically nothing to say what will happen. On the one hand, you might hope that you would get the safer of the two. So if you asked in your application for multiple and in the job script you asked for single, that it would end up with multiple. But I think you risk ending up with the environment variable taking precedence. So if you've asked for single, even though your application will initialize as multiple, it won't actually get that. Oh, you mean the application actually changed the value of this? I don't think so. You can inquire what the level of thread safety is, but I'm not sure. I don't think the MPI standard allows that. A particular implementation, depending on how it's done, potentially it might work, but it wouldn't be portable. I mean, I think MPI in the code, there are ways to inquire the level of thread safety that's provided. So you could write your code with a safety check at the start using an MPI call, which I don't remember what it is, but if you look at the MPI standard, you can find out how to inquire what level of thread safety the library is providing.
The function we just showed before the MPI defining, so it's telling you what has been given.
Okay, so if you check the return value.
Then you should always check.
Yes.
You'll never show.
Yes.
But if you pass, well, if you call MPI any thread and pass MPI thread multiple, for example, but the environment variable says something else, and then you get, for example, single instead of multiple as you ask, will it then return multiple as you is the argument you pass, or will it return single?
No, it's a total.
I think it will return single.
Yeah, then it's up to you. Yes, look in the code, right?
Yes, it polls the library to ask. Because this environment variable is affecting the library, whereas the init thread is basically how you say your application should be run.
Right.
And I agree that, you know, when you have to do things twice, you think, well, did I really need to do this?
Yeah, principle. Yeah. You can use it waiting for an MPI, but it's a mess.
Yeah.
The best is not changing. Makes things simple.
Yes. I mean, depending on the MPI implementation, I mean, there are these locks and there are these overheads. Generally, single, funneled, serialized, there's almost no performance difference between them. Multiple can be, but this improves with, you know, Cray, certainly if you go back a couple of years, multiple was noticeably slower. Now, I mean, there is going to be a difference, but the difference is much smaller because a lot of work's been done to optimize how these locks are done.
The implication using real multiple, I mean, it's something that's really complex.
Some applications do it. I mean, you know, you've got weather codes where they're each computing a column. Yeah. So, I mean, it does happen. But, you know, there can be a performance penalty to it. So, some other MPI flags. Occasionally, you run your code. It takes a certain amount of time. You run it with CrayPat. You know, you do a performance analysis on the code. And you would normally expect that to be slower because CrayPat has introduced extra function calls in order to do the tracing of your application. Sometimes you do this, though, and you discover the application runs faster with CrayPat than without, which is strange. But the reason this can be is quite often it's because if your collectives, if your application, if the ranks are very out of sync, they call collectives at different times. And if the times are too different, then you end up with some sort of buffering and queuing going on. If all the ranks are calling the collectives at about the same time, you can streamline how the collectives are done. So symptoms that this is the sort of thing that's happening is that you see a lot of time in the collectives, far longer than you might expect. And when you instrument the code, it goes faster. If you export this environment variable, it will introduce a barrier before every collective, which essentially is putting them into sync. And that's why the CrayPat was going faster, because it was implicitly putting barriers in order to do the tracing of the application. So if you see that, you should try it. So that's a performance optimization. The rest of these environment variables here have no performance implication. So whilst I say they're for debugging, you could really just set these all the time in every job script. So what will happen is mpitch CPU mask display is telling you something about the binding of the MPI rank by core. It's not telling you where the threads have gone if you've got a hybrid application, but it tells you where the ranks have gone. Having this information is just useful. This will tell you all the MPI environment variables that are set and what values they have. This will